stoichiometry is a really long word explaining a very simple process. And part of the process is being able to convert. So what we learned, how to convert, using dimensional analysis will make your life super easy at this point. So, stoichiometry, from the father of chemistry. In every combustion there is a disengagement of the matter of fire or of light. A body can burn only in pure air, oxygen. There is no destruction or decomposition of pure air, and the increase in weight of the body burnt is exactly equal to the weight of air destroyed or decomposed. The masses involved in chemical reactions, as Lavoisier is able to show us, the mass before has to equal the mass after. This idea allows us to do a process called stoichiometry, which is basically keeping track of what happens. What you got at the beginning, what you got at the end, and how much. So, chemical stoichiometry is merely the study of quantities of materials consumed and produced in chemical reactions. So how much? Now, to keep track of how much, there are a few different ways, but we're going to try to simplify it, make it as simple as possible with how to keep track of how much you have. Yesterday in your chalk lab, you were trying to keep track of how much you had, how many atoms, how many grams of oxygen you had in that chalk that you drew your name with. Keeping track of that is a first step to keeping track using stoichiometry. One portion of this is when you have a compound like calcium carbonate. The percent composition is the percent mass of an element in a compound. All you need to do is you take the amount you have in moles times the molar mass of the element divided by the molar mass of the compound. And just multiply that by 100%, and that gives us what's called the percent composition. N is the number of moles of an element in 1 mole of the compound. So if we had C2H6O, ethanol, looks kind of like a dog. Here's its head right there. The ethanol dog's got a molar mass of 46.07 grams per mole. It's not really a dog, it just looks like one. If we want to know the percent carbon, we know in the formula we've got 2 moles of carbon per 1 mole of ethanol. 2 of these per 1 mole, or 2, sometimes people think of them as atoms per molecule. That works okay in this case, but technically it's the mole per 1 mole of compound, so it's a ratio. Then you multiply by the molar mass of carbon divided by the total molar mass of the compound. To do hydrogen, same setup, except it's 6, and the molar mass of hydrogen is 1.008. So there's the 6. That comes from the periodic table. Oxygen, going to be 1, 16 comes from the periodic table. Looks very similar in the setup. So that's percent composition. Okay, one of my favorite things to do if I have a really easy problem. So it's just a percentage, the amount. So if you look at the percentages, you can see that this compound is 52.14% carbon by mass. It's only 13.13% hydrogen by mass. But if you look at the ratio, it's 6:2. So the ratio, again, the amount in moles doesn't necessarily tell us the percent composition. So that's what we have for percent composition. This formula here, can apply it to any formula you have. If you add up all the percentages, you should get 100%. So this is the way you double check your work. Okay, if you get like 5,000%, you did something wrong. Go back and start again. Mass percent. Here, if you wanted the mass percent of chlorine, you got 2 in CCl2F2. 2 times the molar mass of Cl divided by the molar mass of CCl2F2. So again, that's the picture. Got two of these in the molecule. Here's the whole molecule. Mass of this divided by mass of this, and you got two of those, so that's why it's the mass of the whole thing, two of those. So let's look at stearic acid. Stearic acid's got a couple more than ethanol, but it is a principal component of saturated fat. To calculate the percent composition, what I would like you to do, using the formula you just wrote down, please try to calculate the percent composition of each of the elements in stearic acid. You'll have about 1 minute to come up with your answers. You can write them down. Ready, go. And I know if you have the PowerPoint, don't look at the slide that has the answer, of course, to help you out, unless you want it. It's your choice. Still cool. Yeah, I love your shirt. I don't know if it's possible, but yeah. Oh, that's fine. Let me see if I have one. I mean, I'm sure I can arrange that another time. This one, if the batteries work, you can use it today. You have to be aware, part of the AP test uses calculators, this is fine, and the other part doesn't use them at all. So that's totally fine. Use it on the test, just heads up. But I do need that back today, and then I can give you a signature and take care of it after school or after class or at the end of class, something. All right, now we took a little bit longer than a minute. The one thing about these problems, if you can set it up once, you can set it up twice, you can set it up 3 times, you can do them and do them over and over again, hopefully. If you set it up wrong the first time, you're in bad shape the whole time. So let's look at the setup, make sure we've got at least one of these percent compositions for one of these 3 elements. So here's our formula. Okay, the first step that usually takes the longest is just the molar mass of the entire thing. So you add up the masses of all 18 carbons, 36 hydrogens, and 2 oxygens. Remember to use the precision in the periodic table, the AP periodic table for that. Then percent carbon, you just take 18 times the molar mass divided by the total hydrogen and oxygen. In an ideal world, you'd add them all up and they'd equal 100.00%. Questions or clarifications on any of the steps, formulas, what was done? What was done? These type of problems, you'll get faster at them by practicing some of them. The hardest part usually is doing that and then setting it up, and then you're golden at that point. So these are the answers they would be looking for on a test. Here you put them in boxes. Also showing your work is important for all credit and partial credit, things like that. Now, we talked a little bit about mole ratios. To revisit mole ratios, it's important to know the mole-to-mole ratio between 2 of the substances in a balanced equation. So a mole ratio shows the ratio between the 2 substances, just 2 substances, in a balanced equation. The coefficients of the two substances in the equation show the mole ratios. The mole ratio is a conversion factor central to stoichiometry. It is probably one of the most important conversion factors that involves stoichiometry. You know all the other ones. This is the only thing you don't know right now. And with this, you can do what's called stoichiometry. To write mole ratios, you've got a balanced equation here. Okay? A mole ratio is just the fraction of one of the items in the equation to another. So one of these might be between iron and oxygen. The ratio between iron and oxygen is 4 to 3. 4 iron to 3 moles of oxygen, or 3 moles of oxygen to 4 moles of iron. These two both equal each other, and this is always equal to this for this balanced equation. So this to this is a conversion factor that is true for that balanced equation, and will always be true for that balanced equation. Between iron and iron oxide, 4 to 2 or 2 to 4. Depending on what conversion factor you're looking for, both of them are exactly the same. So you can relate this to this, this to this, and you can also relate your iron oxide to your oxygen. So what would be the ratio between oxygen and the iron oxide? 3 to 2. So 3 moles of oxygen, 2 moles of iron oxide, or you can again write it the other way if need be. To use the mole ratios in a calculation, this would be a sample question. How many moles of the iron oxide are produced when 8 moles of the iron react? So to do this, we have the 8 moles of iron. To determine how many moles of Fe2O3 we need, 8 is proportional to 4 here. 8 is proportional, 8 moles of iron is proportional to 4, that's double that. So 2, double that, there would be 4 moles. That's a way of setting up the ratio, looking at the equation and inspecting it. So how to show this using proportions, you've got 4 moles of iron to 2 moles of iron oxide. That's the equation. You start with 8 moles of iron. That's what you have. You use one of these two. Which of these two has iron in the bottom, left or right? The right one. So you use this here down below to find out your moles of iron oxide. So what you have is here, what you have goes on the bottom, what you want goes on the top. 8 times 2 divided by 4, and that equals 16 over 4, which equals 4.0 moles of Fe2O3. Okay? Now, you can sometimes see it just by the equation, by inspection. You can always do it by dimensional analysis. Okay? And you can do this quicker and quicker every time you do it. So the more practice you have, it's like a skill. Faster, faster, faster you will be. Let's look at another calculation here. I'd like you to try to determine how many moles of iron are required to react with 12 moles of oxygen. Okay? You can solve this any way you want. If you want to use dimensional analysis, that would be what I would recommend. Okay? So just don't say the answer out loud. When you're done getting your answer, you can check with the person next to you. You're welcome to help each other out if you don't know where to start. Ready, set, go. right, let's look at moles of Fe. All right, the answer should be 16.0 moles of Fe. Okay, how you got that? Again, you've got your mole ratio. Two possible options. Either of them are available at any time because you got that balanced equation. Now, what if your equation wasn't balanced? Yeah, balance it first. If you don't balance it, you're out of luck because you can't do this. So, 12 moles of O2 is what you have. You put that down first. What do you want in the problem? Moles of Fe. So that goes here. Now, in this case, you got this unit on the top. What unit do you want on the bottom? Moles of O2. So that's why you use this. Moles of O2 on the bottom, moles of Fe on the top. And then you find out, okay, there's the 3 in front of the O2. That goes here. The 4 in front of the Fe. That goes here. Okay? So I do the units first, do the numbers last. If you can get the units to cancel out, your answer will be right as long as you don't put numbers in weird places. So the numbers match with the unit. So 12, units cancel out. Okay, 48 divided by 3, 16.0 moles of Fe. Okay, 3 significant figures here because mole ratios are exact counting numbers. Okay? All right, now let's try this one. Now let's try this one. Give you a 30-second head start. 30 seconds only. All right. 30-second head start. This one's a little harder to do in your head, although some of you are trying. So here we got 0.43 moles of Fe2O3. Okay, here's our ratios. Either of these, just fine. What we have is right here the 0.65 moles of O2. That's what we have. So always pay attention to that. And what we want is right here. So what I want is there. What I have is here. So we plug that in down there. Woo, that over there. That's all you got to do every time. There it is. There it is. And then plug in the conversion factor that works. If the units cancel, you're good to go. Yay, they do this time. I didn't make another mistake. It's good to go. And then multiply it out. So that's calculation using mole ratios. Okay? All right. Now let's look here at number 4. Let's look at the question first together. What do you have? 0.65 what? Moles of what? O2. It is important that it's moles of O2 and not moles of Fe, of course. What are you trying to find out? Grams of Fe. So this is a little bit different. You have moles and you want to find grams, but you got moles of O2. Okay. So any ideas on what you would do to get this? Okay, use the mole ratio. Use the mole ratio. And then once you have the moles of Fe2O3, how do you get it into grams? Okay. All right, molar mass. Molar mass. So, we got this. We want to find grams. The ratio we know is the 2 to 3 between the iron oxide and the oxygen. The mole ratio relates moles between different substances. Molar mass relates mass to moles for only one substance. So you can only use molar mass if you have, again, one substance. So we know the molar mass of Fe2O3 is 159.70 grams. We can calculate that. So how to set up the problem. There's our moles of O2. We first use the mole ratio to get it into moles of Fe2O3. And then we use the molar mass to get it into grams of Fe2O3. So this is the only new step. This is what you've done before, going from moles to grams. The units cancel. The 2 and the 3 come from the balanced equation. And the grams of Fe2O3 comes from the what table? Periodic table. And it's always per 1 mole. It's based on the formula. It's always based on the formula you have. That's why it's per 1 mole. So once you have all of the units canceled, you just multiply it out and divide, in this case, by 3. So 207.61 grams divided by 3. So using mole ratios. Using mole ratios, this is the last step. How many grams of iron are required to completely react 246.78 grams of O2? So in this problem, we have what? Grams of O2, and we want what? Grams of Fe. So same equation. We're trying to go from grams of O2 to grams of Fe. These are all the things we know. We know the ratio between Fe and O2. We know the molar mass of O2. We know the molar mass of iron. And that's what we're given. So using those conversion factors, you don't have to, again, recalculate them. I'd like you to set up this problem using dimensional analysis. Try to determine how many grams of Fe would be required. Okay? You can do this in a group of up to 4 people at your table. Help each other out. Make sure everyone can get the same answer for this particular problem using this information. I'll give you about a minute and a half to go through this problem here, and then we'll check our answer and see how we did. If you need help or are lost on any of it, please just raise your hand or look at me for a really long time, and I might be able to tell that you need help. Okay? If you're on, don't want to raise your hand. I'll be coming around to help you out. Try to do this using any techniques, but dimensional analysis is preferred. like the person that is closest to the club at your table, you're going to be the spokesperson for your table. You can say any answer you want. It's your answer that might be better. All right. Spokesperson for your group is closest to the club, right? Closest to the club. So when I point to your table, I'd like you to say your answer out loud and proud, no matter what the answer might be. Okay? Are you ready? Here we go. 5, 4, 3, 2, 1. Yep. Thank you. Yep. 574.28. Yep. Yep. Yep.
574.28 grams of iron.
Over here. Little uncertainty there. All right. Yep. All right. So let's see how we did. Everybody agreed on that answer? That might be a great thing. I forgot about your table. Yeah. Don't worry, you'll be first next time. All right. I didn't forget about you. I'm just intentionally leaving you to the next time. All right, so we set it up. Here's our ratios. Okay, then we plug in our numbers last. There we go. Okay, if you multiply it out, top first, then bottom, it looks like this. And 574.28 grams of iron. Good job. Give your friends at your table a congratulations or a high five. All right, now we had 100% success in a group of 4 or 3. So we want to make sure we can have 100% success in a group of 1. Because on the AP test, we don't have group work, unfortunately. But the cool thing is, points to remember, first of all, balance the reaction equations. If it's not balanced, stoichiometry is like useless. Because all your answers will be wrong 100% of the time. So balance the reaction equation. If you balance it wrong, then you use the wrong equation the whole time. It's kind of annoying. But balance it first. Okay? To go from grams of A to grams of B, you do not go straight through. Okay, you will fail every single time. So, if you want to go that way, there's the door. You can go to the counseling office and talk to them. Don't do that. 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 That's my encouragement for you. Now, convert grams of compound A into moles. So you always want to go through the mole. Use the mole. To do that, use the molar mass in grams per mole. Okay, read the coefficients as moles in the balanced equation. Use the mole ratio to get to compound of B, whatever B happens to be. So if you're trying to go from A to B, it's the ratio between A and B. And then convert moles of B into grams. Winner, winner, chicken dinner. So use the molar mass of B. Don't use the molar mass of A when you're using B. Those are these small details that make life easy for you. Now, one thing about the mole ratio to make sure you got the numbers correct. Okay, keep track of the units is very important. Another way to help you out here is the mole ratio. Okay, this always is what you want, which in this case is B, over what you have. So it's still very similar to just going where you want to go. So if you're going from A to B, okay, if you're going to A to B, it's the ratio of what A is to B. So if the coefficient in front of A was 2 and in front of B was 5, this ratio here would be 5 over 2. So that's just an example. Okay, again, keeping track of the units is the best way, but as you do it more and more, you'll see a pattern emerge in stoichiometry. So this here is another graphic showing the same process here, how you get from one to the other. Okay. Now, since we are dealing with moles, I sometimes like to bring in my favorite animal here. So here's my mole / hedgehog, but we're not sure what he is. But now this is a really good looking mole. And this mole here starts right here. And if you go from grams of this to grams of that, there's something that happens. So this is like the ground. The mole wants to get from here to here. Now moles do not go on top of the ground very often. They always try to go under the ground. Now the reason why is you want to go under the ground and use the mole. This is called the mole tunnel. So the mole crawls through here, digs back up, and pops his head up. He's safe. And if you want to go the other way, you can dig down and go this way and come back up on the other side. Yay, mole's happy. Now, this is what happens. If you try to go across here, there is a very large guillotine that chops the mole's head off. And the mole dies. All right, so that's what I meant by fail, sort of, okay? There's your mole example so you don't forget that. All right, now. Let's look here at an example problem of methanol. Methanol burns in air according to this equation. Okay? If 209 grams of methanol are used up in the combustion, what mass of water is produced? So, first things first, what do you have? 209 grams of what? Methanol. What are you trying to get? What do you want? Water. What about water? Grams of water. Very good. So that's how you set it up. I'd like you to calculate the exact mass of water that would be produced in this reaction. Ready, set, go. No guillotines, please. And if you don't know which one is methanol, logically deduce from the other ones. It is a trick. say wild sockeye salmon sometimes has a darker color. If you have artificial... It's a good deal at Costco. Some salmon is artificially colored to make it look like it is healthier. It's good stuff. It's worth it. Let's look at setting this up here. Here we got the molar mass, got the coefficient, and then the molar mass of water. What's wrong with this setup? What's wrong with this setup? What's wrong with it? Somebody who did this was extremely lazy. Round it. Round it on these suckers. Okay? You do not want to round anything until your final answer, and then you can round to sig figs. So this person assumed that they could just round the molar mass anytime they wanted to. And this one here, oh, they only have 3 sig figs in the first one, so might as well round it. And look at what happens to their answer. Their answer is wrong. Okay? What is the actual correct answer? What is the actual correct answer supposed to be? 235.0 what? 02? Now, how many sig figs do you have here? How many are you supposed to have in the number? Okay. So in this number here, there are 3 significant figures, and when we talk more about those, we'll know that these 3 are significant. So when these are both rounded, they both round to 235 grams of H2O. So the good thing is, even though the person got lazy, they still would have gotten the correct answer. And we'll learn about that when we talk more about significant figures. So right now, both would be acceptable answers, although you don't want to round the molar mass when you're doing calculation problems. Okay. When you're doing problems without your calculator, we'll learn to round and estimate quite a bit. So here's another practice problem with acetylene. Acetylene gas, C2H2, burns in the oxyacetylene torch for welding according to this equation. The question would be, how many grams are burned if the reaction produces 75.0 grams of CO2? what I would like you to do is set this up without numbers. Set it up without numbers as quickly as possible. Set it up with units and no numbers. See if you can set it up within 30 seconds or 1 minute. So set up your dimensional analysis without the numbers, except of course the 75. Same thing without the numbers. You don't actually have to solve it, just set it up. All right. At this time, we're going to show how to set it up without solving it completely. So in this one here, we produce 75 grams of CO2. That's what we have. How many grams of C2H2 are burned? That's what we want. So to set it up here, we've got grams of CO2. We want to get to grams of C2H2, so grams of CO2, 2 moles of CO2. That's going to be the molar mass, which I don't know. And then CO2, moles of CO2. We want to get it into moles of C2H2. That's the mole ratio. Then in 1 mole of C2H2, this is the grams of C2H2, which again, this would be from the periodic table. That would be from the periodic table. We've set it up completely without the numbers. Now, the one ratio we can get without too much problem is the mole ratio right here. What goes in front of the CO2 now? 4. 4's in front here. 4 goes in front. C2H2. There's a 2. There's your 2. And then all we need is the molar mass of CO2 and C2H2 to get our final answer. All the units cancel. We could change our color just for fun. Oh, better color than that. Choose a blue. May not be visible. There we go. That cancels, that cancels, that cancels that. That cancels that. And we're left with grams of C2H2. The triangle represents the molar mass of CO2, and the circle represents the molar mass of C2H2, because sometimes even chemists, when they do stoichiometry, get tired or lazy. And we've done a few problems so far. You should be able to do many of these problems, similar setup. And there's all the numbers, 44.01, 26.036, 2 to 4 ratio. We set it up correctly. And that should be our final answer. All right, combustion reactions like this here can easily be predictable. There are multiple reaction types that we need to be familiar with in chemistry. The first one is called a synthesis reaction. Second one is called decomposition. Third one is called a single replacement. Fourth one is called a double replacement. And the fifth one is called a combustion. 5 fingers, 5 reaction types that you should be familiar with. We're going to go through each of these in order to make it easy. First one is synthesis. For a synthesis reaction, that is 2 things or more things coming together to make one compound or one thing. So, A and B going together to make AB, that's synthesis. Sometimes this is also called combination. They combine together to make something new. Synthesize means to make. So synthesis is to make something different. Here you can even have something like this coming together. Again, it can be a compound and an element or 2 elements coming together to make a new compound. It's a combination of 2 or more substances to form one compound. A good example is chlorine gas is passed over a piece of sodium metal, producing solid sodium chloride. This would be, in words, what you would expect for a synthesis reaction. You start with chlorine gas, which is an element, sodium metal, which is a element, and produces solid sodium chloride. To write this equation, chlorine gas, what's the formula for chlorine gas? Cl2. That's right. Cl2, because it is diatomic, it's part of our 7 and 7. Sodium, to make sodium chloride, and then after you write the formulas, you balance it with the coefficients. Here's a picture of that reaction happening. It gives off an incredibly bright white light and produces salt in this reaction. Decomposition. Decomposition, kind of the opposite of synthesis. One thing breaking up into more. Okay, oftentimes it breaks into its elements, but it could break into another compound and an element, like this one here. Again, these are generic letters. Okay, generic letters, not actual elements here. So when it's broken down, usually requires energy for this to happen. That's an important thing about decomposition. Usually requires energy for this to happen because the breaking of bonds requires energy to be added to separate those particular bonds. Anytime you're breaking bonds requires energy to be added. So this usually requires energy for it to proceed. A good example of this, powdered ammonium dichromate is strongly heated, producing heat, nitrogen gas, water, and chromium-3 oxide. To write this equation, you would have ammonium dichromate, strongly heated, and on the product side, you'd have nitrogen gas, water, and chromium oxide, like this. This is powdered ammonium dichromate. It's a solid. There's the ammonium. There's the dichromate. Net charge is 0. Nitrogen gas is also diatomic. Water, and then chromium-3 oxide, making sure that is a neutral formula before you write it. And the last step is to balance the equation. That's a decomposition reaction. Picture of this reaction happening here. This is called the Volcano reaction. It looks just like a volcano when this reaction occurs. This decomposition reaction produces quite a bit of heat as well, but requires a lot of heat to get started. So the reaction does not start, requires a lot of energy. The next type of reaction is known as the single replacement reaction, also called a single displacement reaction. Okay. So for this reaction here is often known as the star reaction. So here is one of the examples of how it could be written. A plus bx makes ax plus b. The A here stands for Aaron Paul. He happens to be a Emmy Award actor in one of the stars about a chemistry teacher that makes methamphetamine, which we'll talk about later. Breaking Bad is what it's called. Not exactly age appropriate for under the age of 18, but if you've seen it, it kind of is funny and has some good chemistry in it, actually. But the next famous person that begins with the letter B is Ben Roethlisberger. And you may not know, but Ben Roethlisberger is in love with Xena, Warrior Princess. And you may not know this, but Ben and Xena, they were together for quite a while. And you may not know the gossip and the story on this, but in the news, all sorts of things happen. And one thing that happened was Aaron Paul. Oh yeah, they were very close. You wouldn't know this because Ben forgot to wear a helmet riding his motorcycle, but that's a whole other story. So Aaron Paul was so attracted to Xena, Warrior Princess, that he came in and busted up their relationship. And whoop, pushed away Ben Roethlisberger. And now, even though you don't know this, Aaron Paul and Xena, Warrior Princess are so tight. They're never separated. This is called a single replacement reaction. What's wrong with Aaron Paul? I mean, he's a good-looking guy, right? Oh, yeah, he acts like a drug dealer. Come on. All right. He's a good actor. He's really not the scum of the earth. And Xena Warrior Princess, she's just a strong woman. I mean, some people like that. So, long story short, there's a single replacement reaction. Easy way of remembering it. You could probably invent your own single replacement reaction for almost any Hollywood star, unfortunately. But invent your own is probably better than mine. I just made that up for fun. All right, so one element is replaced by another in a compound. It's pretty simple. One thing replaces another. Compound is usually an ionic compound. So, an example of this, a piece of magnesium ribbon dropped into hydrochloric acid, generating hydrogen gas and aqueous magnesium chloride. So, the magnesium is dropped in with the hydrochloric acid. There is a switching of ions. So, in this case, the magnesium ribbon is solid magnesium. Hydrochloric acid, does anyone know the formula of hydrochloric acid? HCl, very good. Generating hydrogen gas. Hydrogen gas's formula? H2, and aqueous magnesium chloride. Magnesium chloride is a little harder because you got to keep track of the magnesium has a 2+ charge. The chlorine has a 1- charge, so it's MgCl2. Here's the equation. Once you write the formulas, you then use coefficients to balance it out, and that's all you got to do in a single replacement. So that's an example of another type of equation. Here is the magnesium put into hydrochloric acid, and see these little things here? What do we call these? Bubbles. We can also call it an invisible gas called hydrogen. But these are bubbles. This is evidence that gas is being produced in a reaction. Most of the time, you don't see the gas. So if you say, oh yeah, gas is produced, what's it look like? I don't know. Bubbles. There you go. Bubbles are good evidence, okay? So just be aware of that. If you don't see the bubbles, you probably didn't get a gas. And if you did, it's colored, that's a problem. Colored gases are usually toxic, just as a heads up. So clear gases may not be as toxic. Double replacement. This here, it's got a great story. I don't have good pictures for it because, as you might know, I have another friend named Abe. Now, Abe and Xena Warrior Princess, they were going out. Aaron Paul got the boot. Now, Abe and Xena were going out, and Brad and Yasmin decided to join them because Brad didn't know what to do with his life. I mean, Brad Pitt. So, Yasmin and Brad, they decided to go out on a date. They went out on a date. They were looking across the table at one another, and all of a sudden, Abe decided, you know what, Yasmin's a little strong for me. I'm sorry, Xena's a little strong for me. I don't know what to do. Yasmin was giving him eyes, so he decided maybe, you know, we would just swap. And Brad really had no clue what was going on, and he thought Xena Warrior Princess was his dream girl, and so they just swapped. It's a double date reaction. I mean, double displacement reaction. Easy way of remembering it. This happens on probably 99% of shows that they used to have on TV. I don't know if they still do because I don't watch it very often. But they have these shows. Third wheel is a single replacement reaction, but double displacement are other shows. Yeah, I don't know what this is that happens on TV, but it happens all the time. I captured the castle, all right. I don't know what that is. All right, cool. So, happens all the time in the news, probably too much. If you don't watch TV like that, then you can just imagine it's a swapping of partners in this case. Maybe they're dancing instead of dating. Keep it easy, all right? So elements or ions in two compounds are exchanged. The compounds are usually in ionic compounds. So this usually happens with ionic compounds, and this Xena Warrior Princess might be a polyatomic ion made of multiple things, like an oxy-ion, right? It might not just be like a simple one. So it could be something much larger. X could represent something not just an atom, but a polyatomic ion. So here's a good example of it. We saw this on the first day of class. Sodium iodide and lead-2 nitrate solutions are mixed to produce lead-2 iodide precipitate. Now, what color was the precipitate on the first day? Yellow. Lead-2 iodide is yellow. This is the equation for it. The solid, lead-2 iodide, was yellow. Here's our aqueous solutions, and here's our aqueous sodium nitrate, which was clear and colorless as well. So this here looks like water, looks like water, looks like water, yellow. Now, the really fun thing would be on the first day if I did two aqueous solutions and poured them together, and it went from looks like water, looks like water, looks like water, looks like water. You'd have been like, oh yeah, exciting. Now that's actually part of chemistry, but the exciting part is the solid being produced here. Looking like this. Here's a cool picture of it. The solid is appearing as you're pouring it in. Pretty cool looking. Next type of reaction, combustion reaction. Now for a combustion reaction, we have to have a demonstration because we can't just talk about it. So where did I put my goggles? Make sure I've got my goggles. I did not put them where I thought they were. From my face. Combustion reactions often take a small amount of energy to get them started. Once the combustion reaction has begun, it is what is called an exothermic reaction, produces a large amount of heat which can be observed. This particular reaction here is a fuel called isopropyl alcohol. You should not do this at home because your tables at home are not made of the material here that can allow this reaction to proceed. Now, a couple things that are interesting about that reaction here is if you take isopropyl alcohol and you put it inside of a container like this, isopropyl alcohol in a combustion reaction is the fuel. A combustion reaction is always represented by a few things that are almost always present. The first thing is a fuel. The second thing is what is known as oxygen. In the air, we have about 20% oxygen. And oxygen is necessary for the combustion reaction to proceed. Two things that are produced. Heat is one, energy is produced. An exothermic reaction is what it's called. And two of the products that are also produced, which are invisible gases, include carbon dioxide and water. Those are both invisible gases, not visible. However, you do see something when you burn or combust a material. So this reaction here is a combustion reaction, although this one is a little bit different. So let me just show you what I told you really quickly so you don't miss that. Combustion reactions involve a fuel, CXY, CXHY plus O2, making CO2 and H2O. You can also have a fuel that contains oxygen. So in this one here, we had a fuel that had oxygen, carbon, and hydrogen in it called methanol. Combustion is not limited to just hydrocarbons, although that's the easiest one to remember at this point in the course. Molecular oxygen combines with a hydrocarbon to form carbon dioxide and water. When a hydrocarbon comes in contact with molecular oxygen at the correct ratio with the correct amount of energies, it does produce carbon dioxide and water. The carbon comes from this, the hydrogen comes from that, the oxygen obviously comes from that. If you didn't have a hydrocarbon, you could still have a combustion reaction, and we'll talk more about those as we go. This is a simple example. A hydrocarbon contains carbon and hydrogen, as its name definitely shows us. So the last thing to do someone didn't want their name here. Take a small amount of a match, or a piece of paper in this case. Small ignition source. And that, ladies and gentlemen, is a combustion reaction. The same fuel, the same oxygen, but it didn't react the same. So that has to do with what is called kinetics, or the rate of a reaction, and the reaction happened at a different rate. So when we get to that, we will again revisit that type of demonstration here. So liquid ethanol is burned in air. This demonstration could also be done with liquid ethanol. Okay, ethanol is the dog-looking molecule we saw earlier today. Okay, C2H5OH is often how it's written. It's an alcohol. This OH here represents a hydroxyl group, or the part that makes it an alcohol. Oxygen is the air, part of the air that's important in this reaction, producing carbon dioxide and water. All that you'll be given is this information here. So what you have to remember is that it needs oxygen that comes from the air and produces carbon dioxide and water for a combustion reaction. So those are things here that we can remember for the reaction. So here's another picture of a different combustion reaction here. You'll notice the colors. God bless you. The colors show, again, different energies of the flame. Okay? And here's another picture of combustion. Ice cream. And this looks like ice cream, but this is actually another chemical reaction here. So at this time, I'll give you some time to work on your homework. Hey, quiz tomorrow is on nomenclature. Hey, you will be able to use your ion list on the quiz, as long as you don't have all of the rules for how to name things on that list, which would be considered cheating. So don't do that, please. Nomenclature, quiz tomorrow. In your lab manual, you got lab 2. Bring that tomorrow as well.